Tonight, we're going to confront one of the deepest mysteries hiding inside every atom in your body. Right now, trillions upon trillions of electrons are hovering near positively charged nuclei, attracted to them with enormous force. And according to everything classical physics tells us, those electrons should spiral inward and crash. Every single atom in existence should have collapsed long ago. You, the ground beneath you, the stars, all of it should have been destroyed in a fraction of a second. But it didn't happen. Atoms are stable. You're still here. And for decades, this simple fact tormented the greatest minds in physics, because no one could explain why. The answer, when it finally came, didn't just solve the problem. It dismantled our entire understanding of reality. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with a picture you've probably seen 1,000 times. An atom. A small dense center, and around it, tiny particles moving in neat circles, like planets orbiting a star. This image is everywhere. It's on the covers of science textbooks. It's on the logos of energy companies. It's on the walls of physics classrooms. If you close your eyes and picture an atom, this is almost certainly what you see. A little solar system, neat, orderly, elegant. And it feels right, doesn't it? It makes intuitive sense. You look up at the night sky and you see the moon orbiting the Earth orbiting the sun pulling everything toward it with gravity while the planets circle endlessly around. So when scientists in the early 1900s were trying to figure out what atoms look like, it was only natural to imagine something similar happening at the smaller scales, a heavy center, light things going around it. Same logic, just scaled down. The nucleus of an atom is positively charged. It contains protons, each carrying a positive electric charge, along with neutrons which carry no charge at all. The electrons surrounding the nucleus are negatively charged, and one of the most fundamental laws of electromagnetism says that opposite charges attract each other. Positive pulls on negative, negative pulls on positive. The force between them is described by something called Coulomb's law, named after the French physicist Charles-Augustin de Coulomb, who formulated it in 1785. Coulomb's law tells you exactly how strong the electric force is between two charged objects. The force depends on two things: the size of the charges and the distance between them. The bigger the charges, the stronger the pull, and the closer the charges are, the stronger the pull. In fact, the force increases dramatically as the distance decreases. If you cut the distance in half, the force doesn't just double, it quadruples. If you cut the distance to a third, the force becomes 9 times stronger. This is what physicists call an inverse square law. The force grows as the square of the decreasing distance. This is the same mathematical relationship that governs gravity. Newton's law of universal gravitation follows the same inverse square pattern. Cut the distance between two masses in half and the gravitational force quadruples. So when you look at the atom, you see the same mathematical structure as a planetary system. A central body pulling on orbiting bodies with an inverse square force. The only difference is that in the solar system, the force is gravity, and in the atom, the force is electromagnetism. But the underlying mathematics looks the same. That's why the planetary model felt so natural. It wasn't just a guess, it was built on real mathematical similarities between two systems. In 1911, a physicist named Ernest Rutherford performed one of the most famous experiments in the history of science. He directed a beam of alpha particles, which are essentially the nuclei of helium atoms, at a thin sheet of gold foil. Most of the alpha particles passed straight through the foil as if it weren't there, but a small number bounced back at sharp angles. Some came almost straight back toward the source. Rutherford later said, "This was as if you fired a 15-inch artillery shell at a piece of tissue paper and the shell came back and hit you." This result was shocking because at the time, the prevailing model of the atom was something called the plum pudding model, proposed by J.J. Thomson. In Thomson's model, the atom was a diffuse sphere of positive charge with electrons embedded throughout it, like raisins scattered through a pudding. If atoms were really like that, the alpha particles should have passed through with only slight deflections. There would be no concentrated mass to bounce them back, but they did bounce back. And the only way to explain that was if the positive charge and almost all the mass of the atom were concentrated in an extremely tiny, dense core, a nucleus. Rutherford calculated that this nucleus was roughly 100,000 times smaller than the atom itself. To put that in perspective, if an atom were blown up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the center of the field. The rest of the stadium would be empty space. This was a revolutionary discovery. It told us that atoms are mostly nothing. Almost all the mass is in this tiny nucleus, and the electrons exist somewhere in the vast empty space surrounding it. And so the natural picture emerged. The electrons orbit the nucleus the way planets orbit the sun. The electromagnetic attraction between the positive nucleus and the negative electrons provides the centripetal force needed to keep the electrons moving in circular paths, just as gravity provides the centripetal force that keeps planets in their orbits. This became known as the Rutherford model, or sometimes the planetary model of the atom. It was intuitive, it was elegant, and it was built on solid experimental evidence. The only problem was that it was fatally, catastrophically wrong. Not slightly wrong, not wrong in the details, wrong in a way that predicted the immediate destruction of all matter in the universe. To understand why, you need to know something about a set of equations written down by a Scottish physicist named James Clerk Maxwell in the 1860s. Maxwell's equations are one of the greatest achievements in the history of physics. They unified electricity and magnetism into a single framework called electromagnetism, and they predicted the existence of electromagnetic waves, which turned out to be light. Maxwell showed that light is an electromagnetic wave, a ripple in electric and magnetic fields propagating through space at about 300,000 kilometers per second. Maxwell's equations didn't just describe static charges and steady currents. They described what happens when charges move, and especially what happens when charges accelerate. And here's the critical point. According to Maxwell's equations, any charged particle that accelerates must radiate electromagnetic energy. This is not a suggestion. It's not a tendency. It's a fundamental, inescapable consequence of the theory. If a charged particle is accelerating, it radiates energy in the form of electromagnetic waves. Period. No exceptions. Now, think about what it means for an electron to orbit a nucleus. Orbiting is circular motion, and circular motion is a form of acceleration. Even if the electron is moving at constant speed, it's constantly changing direction. And any change in direction means acceleration. This is the same reason you feel pushed outward on a merry-go-round or when a car turns sharply. You're accelerating even though your speed might not be changing because your direction is changing. So an orbiting electron is an accelerating electron. And according to Maxwell's equations, an accelerating electron must radiate energy. It has no choice. The laws of electromagnetism demand it. This creates an immediate and devastating problem. If the electron is radiating energy, it's losing energy. And if it's losing energy, it can't maintain its orbit. It must spiral inward toward the nucleus. Think about it this way. The electron is moving in a circle around the nucleus, held in orbit by the electromagnetic attraction between its negative charge and the nucleus's positive charge. But it's also radiating energy away in the form of electromagnetic waves, getting dimmer and dimmer, losing speed, losing altitude, spiraling closer and closer to the nucleus. As it spirals inward, it gets closer to the nucleus, and as it gets closer, the electromagnetic force gets stronger because of the inverse square law. The stronger force pulls it in even faster. The electron accelerates more, which means it radiates more energy, which means it loses energy faster, which means it spirals inward even more quickly. It's a runaway process, a death spiral. The electron doesn't gently drift inward, it plummets, and the math tells us exactly how fast this would happen. Physicists calculate that an electron orbiting a hydrogen nucleus would spiral inward and crash into the proton in approximately 1/10-billionth of a second. Let me say that again because it's important. 1/10-billionth of a second, that's 0.1 nanoseconds. That's faster than the fastest electronic processors in modern computer chips. In less time than it takes for light to travel a single foot, the electron would crash into the nucleus and the atom would cease to exist. The atom would collapse. Its entire structure would implode. The electron would merge with the nucleus. The atom would shrink from its normal size, about 1/10-billionth of a meter across, to the size of the nucleus, about 100,000 times smaller. Everything we call the atom, the electron cloud, the chemical properties, the ability to bond with other atoms, all of it would vanish in a fraction of a second. And this isn't just a problem for one atom. If this happened to one hydrogen atom, it would happen to every hydrogen atom, and every helium atom, and every carbon atom, and every oxygen atom. Every atom of every element would suffer the same fate. The electrons would spiral into their nuclei, and every atom in the universe would collapse essentially instantaneously. There would be no molecules because molecules are made of atoms bonded together through their electrons. There would be no chemistry because chemistry is the behavior of electrons in atoms. There would be no solid objects, no liquids, no gases, no stars, because stars are made of atoms. No planets, because planets are made of atoms. No water, no air, no rocks, no life, nothing that we recognize as matter would exist. The universe would be a soup of collapsed atomic remnants, tiny dense points with no structure, no complexity, no possibility of forming anything interesting. You wouldn't be here. The device you're using to listen to this wouldn't be here. The Earth wouldn't be here. The sun wouldn't be here. Nothing would be here. And this collapse wouldn't have happened billions of years ago when the universe was young. It would have happened immediately. The moment the first atoms formed, they would have collapsed. There would never have been a universe of stable matter. Not for a single second. This is what classical physics predicted. Not as a fringe idea, not as a speculative hypothesis, but as the direct, unavoidable consequence of applying Maxwell's equations and Newtonian mechanics to the Rutherford model of the atom. two of the most successful and well-tested theories in all of physics, electromagnetism and classical mechanics, when applied to the atom, predicted that atoms cannot exist. Let me emphasize how deeply troubling this was. Maxwell's equations worked. They predicted electromagnetic waves. They explained how light propagates. They led to the development of radio, television, radar. They were confirmed by experiment after experiment after experiment. Newtonian mechanics worked too. It predicted the motions of planets with extraordinary precision. It explained the tides, the orbits of comets, the behavior of projectiles. It had been the foundation of physics for over 200 years. Both theories were spectacularly successful. Neither was wrong in any way that anyone could detect when applied to the macroscopic world. But together, when applied to the atom, they produced an absurd result. They predicted that matter itself was impossible. Something had to give. Either Maxwell's equations were wrong, or Newtonian mechanics was wrong, or the model of the atom was wrong, or some entirely new physics was needed. But no one knew what that new physics could be. Now, it's important to understand that this wasn't a problem that snuck up on physicists gradually. It hit them like a wall. In the years following Rutherford's discovery of the nucleus, physicists immediately recognized the instability problem. They could see it staring at them from the equations. There was no way to avoid it, no mathematical trick to make it go away. If you accepted three things: that atoms have a small, dense positive nucleus, that electrons are negatively charged particles surrounding that nucleus, and that Maxwell's equations govern the behavior of charged particles, then you were forced to conclude that atoms should collapse. Some physicists tried to find ways around it. Maybe the electrons weren't orbiting. Maybe they were stationary, just sitting in fixed positions around the nucleus. But that didn't work either. A stationary electron near a positive nucleus would simply be pulled straight in by the electromagnetic force. Without orbital motion providing centripetal balance, the electron would accelerate directly toward the nucleus and hit it even faster than a spiraling electron would. Others wondered if maybe there was some unknown force, some kind of repulsion that kicked in at very short distances and prevented the electron from getting too close. But there was no evidence for any such force. And inventing forces without evidence is not how good physics works. You can't just make up a new force every time your equations give you an answer you don't like. Still, others wondered if maybe Maxwell's equations didn't apply at the atomic scale. Maybe electromagnetism worked differently for very small systems. But this was a radical suggestion. Maxwell's equations were among the most thoroughly tested and universally accepted laws in all of physics. Suggesting they might fail at small scales was like suggesting that arithmetic might not work for small numbers. It seemed absurd, and yet, in a way, that radical suggestion turned out to be the closest to the truth. Not that Maxwell's equations were wrong exactly. They remained valid and accurate descriptions of electromagnetic phenomena. But the behavior of matter at the atomic scale turned out to be governed by entirely different rules. Rules so strange and counterintuitive that they would take decades to fully work out and that many physicists initially refused to accept. The problem of the collapsing atom wasn't just a technical puzzle. It was a signpost pointing toward a revolution in physics. It was telling physicists, in the loudest possible way, that the laws governing the microscopic world were fundamentally different from the laws governing the macroscopic world. The universe at the scale of atoms did not play by the same rules as the universe at the scale of planets and baseballs and cannonballs. But in the early 1900s, no one knew what those new rules were. They just knew that the old rules predicted catastrophe. And the fact that atoms clearly did exist, that matter was obviously stable, that the universe had not collapsed, meant that something profound and unknown was happening inside every atom, something that classical physics could not explain. The classical picture of the atom was not just slightly inaccurate, it was missing something essential, something so fundamental that without it, the very existence of matter became inexplicable. And finding that missing piece would require abandoning assumptions so deeply held that most physicists consider them self-evident truths about how the universe works. It would require giving up the idea that particles have definite positions and definite paths. It would require accepting that the act of measurement changes what you're measuring. It would require embracing a description of nature that is inherently probabilistic, where you can never predict exactly what will happen, only the probability of different outcomes. All of this lay ahead, waiting to be discovered. But in the first decade of the 20th century, the collapse of the classical atom stood as one of the most glaring failures in the history of physics. A failure that would ultimately lead to one of the greatest revolutions in human thought. There were other cracks forming in classical physics around the same time. The collapsing atom wasn't the only problem. There was the ultraviolet catastrophe, a prediction from classical thermodynamics that an idealized hot object called a black body should radiate infinite energy at short wavelengths. Obviously, hot objects don't emit infinite energy. Something was wrong with the classical calculation. There was also the photoelectric effect, the observation that shining light on certain metals could eject electrons from the surface. Classical wave theory predicted that brighter light should give the ejected electrons more energy regardless of color. But experiments showed that the energy of the ejected electrons depended on the color of the light, not its brightness. Red light, no matter how bright, couldn't eject electrons from certain metals, but even dim violet light could. These problems, the collapsing atom, the ultraviolet catastrophe, the photoelectric effect, were all symptoms of the same underlying disease. Classical physics was breaking down at the smallest scales. The rules that worked so perfectly for the macroscopic world were failing when applied to atoms, light, and the interactions between them. And the cure for this disease would come in stages. It would begin with a tentative suggestion by a German physicist named Max Planck in 1900. It would develop through a bold proposal by Albert Einstein in 1905. It would take a dramatic leap with a Danish physicist named Niels Bohr in 1913. And it would reach its full, strange, beautiful maturity in the mid-1920s with the development of quantum mechanics by Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and others. Each step along this path would chip away at the classical picture of the world. Each step would reveal something new and unexpected about the nature of reality at the smallest scales. And each step would bring physicists closer to understanding why the electron doesn't fall into the nucleus. But all of that was still to come. For now, at the start of the 20th century, the problem stood unsolved. Classical physics said atoms should collapse. Atoms didn't collapse, and no one could explain why. The electron should fall into the nucleus. Everything about classical electromagnetism demands it. The math is clear. The logic is airtight. An accelerating charge radiates energy. An orbiting electron is an accelerating charge. Therefore, an orbiting electron radiates energy. And an electron that radiates energy spirals inward and crashes. There is no escape within classical physics. No loophole, no clever reinterpretation. The conclusion is forced upon you by the equations. And yet here you are, made of atoms, stable, solid, real atoms that have existed for billions of years without collapsing. The hydrogen atoms in the water in your body have been stable since they formed in the first few minutes after the Big Bang, roughly 13.8 billion years ago. They haven't collapsed. They haven't even changed. They're the same hydrogen atoms, with the same properties, the same size, the same energy levels as every other hydrogen atom in the universe. Something is keeping those electrons from falling in. Something is holding the atom open, maintaining its structure, preserving its stability across cosmic timescales. And whatever that something is, it isn't any force or mechanism that classical physics knows about. The answer lies in a completely different way of thinking about nature. A framework so strange that even the physicists who developed it struggled to accept what it was telling them. A framework where particles don't have definite positions until you measure them, where the act of observation changes the system being observed, where certainty is replaced by probability, and where the very question of what is happening between measurements may have no answer at all. That framework is quantum mechanics. And it doesn't just solve the problem of the collapsing atom. It replaces the entire picture. The electron doesn't avoid falling into the nucleus through some clever trick. It doesn't fall because the very concept of falling, of following a definite path, of spiraling inward along a trajectory, doesn't apply. The electron doesn't have a trajectory. It doesn't orbit. It doesn't move in circles or ellipses or any other definite path. At the quantum scale, the rules are different. And those different rules are what make atoms and everything built from atoms possible. But to understand how that works, we first need to understand how the quantum revolution began. Because it didn't happen all at once. It happened in stages, each more surprising than the last, each peeling back another layer of the classical worldview to reveal something stranger and more beautiful underneath. The first crack in the classical worldview didn't come from studying atoms directly. It came from studying something much more ordinary. Heat. Specifically the way hot objects glow. You've seen this countless times. Heat a piece of metal and it starts to glow. First a dull red, then orange, then yellow, then white. The hotter the object, the brighter it glows, and the more the colour shifts toward the blue end of the spectrum. This is called thermal radiation, and every object in the universe emits it. You're emitting thermal radiation right now. Your body radiates infrared light because you're warm. You can't see it with your eyes, but an infrared camera can. The sun emits thermal radiation too, which is why it shines. The filament in an old incandescent light bulb emits thermal radiation when electricity heats it up, which is why it produces light. This phenomenon was well known in the late 1800s, and physicists were trying to develop a mathematical formula that would describe exactly how much energy a hot object radiates at each wavelength. They wanted an equation that would predict the full spectrum of thermal radiation for any temperature. This turned out to be surprisingly difficult. Two physicists, Lord Rayleigh and James Jeans, derived a formula using classical physics. Their formula worked reasonably well for long wavelengths, like infrared light, but at short wavelengths, toward the ultraviolet end of the spectrum, their formula predicted something absurd. It predicted that the amount of energy radiated should increase without limit as the wavelength gets shorter. It predicted that any hot object should emit infinite energy at ultraviolet wavelengths. This was clearly nonsense. Hot objects don't emit infinite energy. If they did, everything around them would be vaporized instantly. You couldn't light a candle without destroying the room. This embarrassing failure of classical physics was called the ultraviolet catastrophe, and it told physicists that something was fundamentally wrong with how they were thinking about energy and radiation. In 1900, a German physicist named Max Planck found a mathematical fix. He discovered that if he made one specific assumption, his equations would produce a formula that perfectly matched the experimental data for thermal radiation at all wavelengths. That assumption was radical. Planck proposed that energy is not emitted continuously, the way classical physics assumed. Instead, energy is emitted in discrete packets, which he called quanta. Each quantum of energy has a specific size that depends on the frequency of the radiation. The higher the frequency, the larger the quantum. Planck introduced a new constant to describe the size of these energy packets. This constant, now called Planck's constant, is extraordinarily small. Its value is about 6.626 times 10 to the negative 34 joule seconds. That's a decimal point followed by 33 zeros and then a 6. It's unimaginably tiny by everyday standards, which is why we never notice the quantum nature of energy in our daily lives. At the scales we experience, energy appears perfectly smooth and continuous because the individual quanta are so small. But at the atomic scale, Planck's constant becomes significant. The discreteness of energy matters. The fact that energy comes in packets rather than flowing continuously has profound consequences for how atoms behave. Planck himself wasn't entirely comfortable with his own idea. He viewed the quantization of energy as a mathematical trick, a computational device that happened to give the right answer. He didn't necessarily believe that energy was truly quantized in nature. He hoped that someone would eventually find a classical explanation that would make the quanta unnecessary. That didn't happen. Instead, the idea of quantization grew more powerful and more inescapable as other physicists began applying it to different problems. The first person to take Planck's quanta truly seriously was Albert Einstein. In 1905, the same year he published his theory of special relativity, Einstein tackled a puzzle called the photoelectric effect. The photoelectric effect had been observed experimentally, and it behaved in ways that classical physics could not explain. When you shine light on certain metals, electrons are ejected from the surface. That much was expected. Light carries energy, and that energy can knock electrons free. But the details were wrong. Classical physics predicted that the energy of the ejected electrons should depend on the brightness of the light. Brighter light means more energy, so the electrons should come out faster. But experiments showed something completely different. The energy of the ejected electrons didn't depend on brightness at all. It depended on the color of the light, which is to say, its frequency. Blue light, which has a higher frequency, ejected electrons with more energy than red light, which has a lower frequency. And here was the really strange part. If the light's frequency was too low, no electrons were ejected at all, no matter how bright the light was. You could shine the most powerful red lamp in the world on certain metals, and not a single electron would come out. But a faint beam of ultraviolet light would knock electrons free immediately. Classical wave theory couldn't explain this. If light were a continuous wave, then a sufficiently bright beam of any color should eventually deliver enough energy to eject electrons. It might take longer with red light, but it should still work if you made the beam bright enough. But it didn't work. Below a certain frequency threshold, nothing happened regardless of brightness. Einstein proposed a bold explanation. Light, he said, is not a continuous wave. It comes in discrete packets of energy, which he called light quanta, and which we now call photons. Each photon carries a specific amount of energy determined by its frequency, exactly as Planck had suggested. When a photon hits a metal surface, it either has enough energy to knock an electron free or it doesn't. If the photon's frequency is too low, its energy is too small to overcome the force holding the electron in the metal, and the electron stays put. No number of low-energy photons arriving one after another will help, because the process is all or nothing. Each individual photon either has enough energy or it doesn't. This was a radical claim. Light had been understood as a wave for over a century, ever since Thomas Young's double-slit experiment in 1803 demonstrated interference patterns that only waves could produce. Maxwell's equations described light as an electromagnetic wave. The wave nature of light was one of the most firmly established facts in all of physics. And now Einstein was saying that light also behaves as a particle, not instead of a wave. In addition to being a wave, light is both. This dual nature, wave and particle, simultaneously, was deeply unsettling to many physicists. It seemed contradictory. How can something be both a wave, which is spread out and continuous, and a particle, which is localized and discrete? This question would haunt physics for decades, and in many ways it still does. But the evidence was undeniable. The photoelectric effect couldn't be explained without photons. Einstein's explanation was confirmed by experiment after experiment. In 1921, he was awarded the Nobel Prize in Physics for this work. Not for relativity, as many people assume, but for explaining the photoelectric effect. Now, two pieces of the puzzle were in place. Planck had shown that energy is quantized. Einstein had shown that light itself is quantized, made of discrete photons. The next piece came from a young Danish physicist named Niels Bohr, and it dealt directly with the problem of the collapsing atom. In 1913, Bohr proposed a new model of the atom that took the idea of quantization and applied it directly to the electron's behavior around the nucleus. His proposal was startlingly simple in concept, though revolutionary in its implications. Bohr kept the idea of electrons circling the nucleus, like planets around a star, but he added a crucial rule that had no precedent in classical physics. He declared that electrons cannot orbit at just any distance from the nucleus. They can only occupy certain specific orbits, certain allowed energy levels. Between these allowed orbits, there is nothing. No intermediate states, no gradual transitions. The electron is either in one allowed orbit or another. There is no in-between. This was not a conclusion derived from deeper principles. It was a postulate, an assumption that Bohr introduced because it worked. He didn't explain why only certain orbits were allowed. He simply asserted that they were, and then showed that this assertion led to correct predictions. The most important part of Bohr's model was his second radical postulate. He declared that an electron in one of these allowed orbits does not radiate energy. This directly contradicted Maxwell's equations, which demanded that any accelerating charge must radiate. Bohr simply said, no. In these special allowed states, the electron is stable. It does not lose energy. It does not spiral inward. It stays where it is indefinitely. This sounds like cheating, and in a way, it was. Bohr was essentially saying that Maxwell's equations, which had been spectacularly successful for over 50 years, simply don't apply to electrons and atoms in the same way they apply to macroscopic charged objects. He was imposing a rule by hand, without deriving it from any deeper theory. But the reason physicists took him seriously was that his model made predictions. Specific, testable, numerical predictions. And those predictions matched experimental data with breathtaking accuracy. Here's how. When an electron jumps from a higher allowed orbit to a lower one, it emits a photon. The energy of that photon equals the exact difference in energy between the two orbits. Since only certain orbits are allowed, only certain energy differences are possible. And since each energy corresponds to a specific frequency of light, and each frequency corresponds to a specific color, Bohr's model predicted that atoms should emit light only at certain specific wavelengths, certain specific colors. Not a continuous rainbow, but a discrete set of sharp spectral lines. This prediction matched something that had been known experimentally for decades, but never explained. When you heat hydrogen gas until it glows and then pass the light through a prism, you don't see a continuous spectrum of colors. You see a set of distinct, sharp lines. Specific wavelengths of light separated by gaps where no light appears at all. These hydrogen spectral lines have been carefully measured by Swiss mathematician Johann Balmer in 1885, and later by Swedish physicist Johannes Rydberg. They followed a precise mathematical pattern, but no one had any idea why hydrogen emitted light at those specific wavelengths and no others. Bohr's model explained it perfectly. His calculated wavelengths matched the measured spectral lines of hydrogen to an accuracy of better than 1/10 of 1%. This was not a vague qualitative agreement. It was a precise quantitative match. The kind of agreement between theory and experiment that makes physicists sit up and pay attention. The model also explained why different elements produce different spectral lines. Each element has a different number of protons in its nucleus, which means the allowed energy levels are different for each element. The specific set of spectral lines an element produces is essentially its fingerprint, unique and identifiable. This is how astronomers determine what distant stars are made of. They analyze the spectral lines in the star's light and match them to the known spectra of elements measured in laboratories on Earth. Bohr's model was a triumph. It solved the problem of the collapsing atom, at least for hydrogen. And it explained one of the longest-standing puzzles in spectroscopy. But it had serious limitations. It worked beautifully for hydrogen, which has only one electron. But when physicists tried to apply it to heavier atoms with more electrons, the predictions became increasingly inaccurate. Helium with just 2 electrons was already problematic. The model couldn't accurately predict helium's spectral lines. For more complex atoms like carbon or iron, it failed almost completely. There was also a deeper conceptual problem. Bohr's model told you which orbits were allowed, but it didn't tell you why. Why those specific orbits and not others? What was special about them? Why did the electron refuse to radiate in these states when Maxwell's equations demanded that it should? Bohr had imposed these rules by fiat. He declared them to be true and showed that they led to correct results. But a rule without an explanation is unsatisfying. It feels ad hoc, like a patch applied to cover a hole without understanding what caused the hole in the first place. Physics doesn't just want to describe what happens, it wants to understand why it happens. Bohr's model described the what, but the why remained mysterious. The missing explanation came from an unexpected direction. In 1924, a French physicist named Louis de Broglie submitted his doctoral thesis. In it, he proposed an idea so bold that the examining committee wasn't sure whether it was brilliant or crazy. They sent it to Einstein for evaluation. Einstein declared it brilliant. De Broglie's idea was simple in concept, but profound in its consequences. He started from Einstein's discovery that light, which everyone thought was a wave, also behaves as a particle. And he asked the obvious mirror image question. If waves can behave as particles, can particles behave as waves? Specifically, de Broglie proposed that electrons, which everyone thought were particles, also have a wave nature. He derived a formula relating the wavelength of this electron wave to the electron's momentum. The wavelength equals Planck's constant divided by the electron's momentum. This is called the de Broglie wavelength. For everyday objects like baseballs or people, the de Broglie wavelength is incomprehensibly small. A baseball moving at 100 kilometers per hour has a de Broglie wavelength of roughly 10 to the negative 34 meters. That's billions of times smaller than the nucleus of an atom. At such tiny wavelengths, the wave nature is completely undetectable. The baseball behaves like a pure particle for all practical purposes. But for an electron, which has a much smaller mass and moves at speeds typical of atomic electrons, the de Broglie wavelength turns out to be comparable to the size of an atom. And at this scale, the wave nature becomes critically important. It's not a minor correction. It's the dominant feature of the electron's behavior. Now, this was a bold hypothesis, and in science, a hypothesis without experimental evidence is just a guess, no matter how elegant. De Broglie had proposed that electrons are waves, but no one had ever observed an electron behaving like a wave. No one had ever seen an electron diffract or interfere with itself. Without experimental proof, the idea remained theoretical. That proof came in 1927, and it came almost by accident. Two American physicists, Clinton Davison and Lester Germer, were working at Bell Laboratories in New York, firing beams of electrons at a nickel target. They were studying how electrons scatter off metal surfaces, a fairly routine experiment. During one experiment, the vacuum chamber cracked. Air rushed in and oxidized the nickel target. To repair the damage, they heated the nickel to high temperature. This heating had an unintended effect. It caused the nickel to recrystallize, forming large single crystals with atoms arranged in regular, orderly rows. When Davison and Germer resumed their experiment, firing electrons at this recrystallized nickel, they found something completely unexpected. Instead of scattering randomly in all directions, the electrons were bouncing off in specific directions, forming a distinct pattern. The pattern looked exactly like what you would expect from a wave diffracting off a crystal lattice. This was the same kind of pattern that X-rays produced when bouncing off crystals, and X-rays were known to be waves. The only way to explain the electron's behavior was if the electrons were also waves, with a wavelength matching exactly what de Broglie had predicted. The electrons weren't just particles bouncing off atoms, they were waves interfering with each other. When the wave crests from electrons bouncing off different rows of atoms lined up, the waves reinforced each other and produced a strong signal in that direction. When the crests and troughs misaligned, they cancelled each other out. This is called diffraction, and only waves can do it. The Davison-Germer experiment was stunning confirmation. De Broglie's hypothesis wasn't just a clever theoretical trick. Electrons genuinely behave as waves. You could measure their wavelength. You could observe their interference patterns. The wave nature of matter was real as the wave nature of light. Davison received the 1937 Nobel Prize in Physics for this discovery, sharing it with George Paget Thomson, the son of J.J. Thomson, who had independently confirmed electron diffraction in a separate experiment. And it cemented one of the strangest truths about the universe. Matter, the solid, tangible stuff we touch and see every day, is also a wave. Not a metaphor for a wave, not analogous to a wave, an actual wave, with measurable wavelengths and observable diffraction patterns. De Broglie's hypothesis, now experimentally confirmed, immediately explained Bohr's mysterious quantization rule. Here's how. Imagine the electron's wave wrapped around the nucleus. If the electron is truly a wave, then as it goes around the nucleus, the wave has to connect smoothly with itself after completing a full loop. It has to form what's called a standing wave. Think about a guitar string. A guitar string is fixed at both ends, and it can only vibrate at certain specific frequencies. The fundamental frequency, the first harmonic, the second harmonic, and so on. These are the frequencies where the wave pattern fits perfectly between the two fixed endpoints. A whole number of half wavelengths must fit along the string. If you try to vibrate the string at a frequency between harmonics, the wave doesn't fit. It interferes with itself destructively and dies out. Only the resonant frequencies survive. The same principle applies to an electron wave wrapped around a nucleus. The wave has to fit perfectly around the circumference of the orbit. A whole number of wavelengths must fit around the loop. If the circumference corresponds to exactly one wavelength, or exactly two wavelengths, or exactly three, the wave reinforces itself and forms a stable standing wave. These are the allowed orbits. If the circumference doesn't correspond to a whole number of wavelengths, the wave interferes with itself destructively. The crest of one pass around the loop cancel the troughs of another. The wave destroys itself. These orbits are forbidden. This is why only certain orbits are allowed. It's not an arbitrary rule imposed from outside. It's a natural consequence of the electron's wave nature. Only orbits where the electron wave forms a stable standing wave pattern can exist. All other orbits are physically impossible because the wave would cancel itself out. Bohr's quantization rule, which he had imposed without explanation, now had a physical explanation. The allowed orbits are standing wave resonances of the electron wave. The forbidden orbits are configurations where the wave nature prevents stable existence. But de Broglie's hypothesis, powerful as it was still incomplete. It explained why orbits were quantized, but it still used the language of orbits. It still pictured the electron as a wave traveling along a circular path around the nucleus. The full revolution came in 1925 and 1926, when two different mathematical frameworks were developed that replaced the entire concept of orbits with something far more strange and far more powerful. The first came from Werner Heisenberg, a young German physicist who was only 23 years old at the time. In the summer of 1925, recovering from hay fever on the island of Helgoland in the North Sea, Heisenberg developed a mathematical framework now called matrix mechanics. Heisenberg took a radical approach. He decided that physics should only concern itself with things that can actually be observed and measured. You can observe the light an atom emits. You can measure the wavelengths and intensities of spectral lines, but you cannot observe an electron orbiting a nucleus. No one has ever seen an electron's orbit. So Heisenberg threw out the concept of orbits entirely. He built his theory using only observable quantities, the frequencies and intensities of emitted light, and the mathematical rules connecting them. The result was a theory expressed in terms of matrices, which are arrays of numbers governed by specific algebraic rules. The mathematics was unfamiliar to most physicists at the time, and the physical picture behind it was obscure, but it worked. It reproduced Bohr's results for hydrogen and went further, correctly predicting the behavior of more complex systems where Bohr's model failed. A few months later, in 1926, the Austrian physicist Erwin Schrödinger developed an alternative approach called wave mechanics. Schrödinger was inspired directly by de Broglie's idea that electrons have a wave nature. He took de Broglie's hypothesis on faith, months before the Davison-Germer experiment would prove it in the laboratory. But where de Broglie had described the electron wave as something traveling along a path around the nucleus, Schrödinger wanted a complete mathematical equation that would describe how the electron wave behaves in 3 dimensions in the presence of any force. He wanted the electron equivalent of Maxwell's equations for light, a universal equation that would govern the behavior of matter, waves the way Maxwell's equations governed electromagnetic waves. Over the Christmas holidays of 1925, while staying at a villa in the Swiss Alps, Schrödinger worked out his equation. He wrote down a differential equation, now called the Schrödinger equation, that describes how the electron wave evolves in the presence of forces like the electromagnetic attraction of a nucleus. The equation was similar in form to equations that describe water waves, sound waves, and vibrating strings. Physicists found it much more intuitive than Heisenberg's abstract matrix formulation. It felt familiar because it used mathematical tools they already knew, and it gave them a picture to hold onto. The solutions to the Schrödinger equation for an electron in a hydrogen atom turned out to be 3-dimensional standing wave patterns around the nucleus. These are called orbitals, and they replace the old concept of orbits entirely. An orbital is not a path. It's not a trajectory the electron follows. It's a mathematical function that exists throughout the space around the nucleus, and it looks nothing like a planet's orbit. The simplest orbital, the ground state of hydrogen, is spherically symmetric. It's a cloud centered on the nucleus, densest at the center and fading gradually outward. There is no orbit, no circle, no ellipse. The electron doesn't travel along any definite path. Instead, it exists as this 3-dimensional cloud, spread out around the nucleus in all directions simultaneously. Higher energy orbitals have more complex shapes. Some look like dumbbells, some look like rings, some have multiple lobes pointing in different directions. But none of them are orbits. None of them represent a tiny ball following a definite trajectory around the nucleus. What does this cloud represent? This is where things get philosophically deep, and where physics entered territory that made many physicists deeply uncomfortable. In 1926, German physicist Max Born proposed an interpretation that became the standard understanding. He suggested that the wave function doesn't describe the electron itself. It describes the probability of finding the electron at any given location if you were to make a measurement. The square of the wave function at any point gives you the probability density at that point. Where the wave function is large, you're more likely to find the electron. Where it's small, you're less likely. But until you actually make a measurement, the electron doesn't have a definite position. It's not that we don't know where the electron is. It's that the electron doesn't have a specific location. The question of where the electron is at any given moment is simply not a meaningful question according to quantum mechanics. This is not a limitation of our technology or our knowledge. It's a statement about the nature of reality at the quantum scale. Classical physics assume that particles always have definite positions and definite velocities at every moment, whether we're looking at them or not. Quantum mechanics says that's wrong. Particles exist in states described by wave functions, and these states don't correspond to definite positions until a measurement forces the issue. Schrödinger himself was troubled by this interpretation. He had hoped his wave equation described something physically real. Perhaps the electron was literally smeared out in space, spread across the cloud like a substance. But Born's probabilistic interpretation won out because it made the correct experimental predictions. Schrödinger's equation and Heisenberg's matrix mechanics turned out to be mathematically equivalent. Two different formulations of the same underlying theory. This was proven by Paul Dirac and John von Neumann. Despite looking completely different on the surface, one using waves and differential equations, the other using matrices and algebra, they gave exactly the same predictions for every observable quantity. This meant there was a single coherent theory underlying both approaches. That theory is quantum mechanics. And quantum mechanics didn't just tweak the classical picture of the atom, it demolished it. The electron is not a tiny planet orbiting the nucleus. It's not a ball following a trajectory. It doesn't have a definite position at each moment. It doesn't move along a definite path. Instead, it exists in a quantum state described by a wave function that assigns probabilities to different possible outcomes of measurement. The entire language of orbits, trajectories, paths, and positions becomes meaningless at this scale. And this is what saves the atom from collapse. The classical problem was that an orbiting electron must radiate energy and spiral inward. But quantum mechanics says the electron is not orbiting. It's in a quantum state. It's not accelerating along a curved path because it doesn't have a path. The concept of an orbit, which was essential to the classical argument for radiation and collapse, simply doesn't exist in the quantum description. Without an orbit, there is no acceleration. Without acceleration, there is no radiation. Without radiation, there is no energy loss. Without energy loss, there is no spiral. And without a spiral, there is no collapse. The atom is saved not by finding a new force that pushes the electron outward, not by discovering a shield that blocks the radiation, but by discovering that the entire classical picture was wrong from the start. The electron never orbited in the first place. It exists in a quantum state, a standing wave pattern around the nucleus, and that state is stable. Not because something prevents it from collapsing, but because the very concept of collapse has no meaning in the quantum framework. The old question of why the electron doesn't spiral into the nucleus turns out to be based on a false premise. It's like asking why the North Pole doesn't fall off the Earth. The question assumes a picture of reality that doesn't match how things actually are. The Earth doesn't have a flat surface with edges to fall off of, and electrons don't follow orbital paths that could spiral inward. Both questions reveal a fundamental misunderstanding of the system in question. But this raises a new question. If the electron is not orbiting, If it exists as a probability cloud spread out around the nucleus, what actually prevents it from being right on top of the nucleus? The electron is attracted to the nucleus. The electromagnetic force pulls it inward. If the electron is described by a probability cloud, why doesn't that cloud simply shrink down to a point centered on the nucleus? Why doesn't the probability cloud collapse, even if the classical orbit doesn't? This is the deepest question of all, and the answer involves one of the strangest and most profound principles in all of physics. A principle that places a fundamental limit on what can be known about the universe. A limit that is not a consequence of imperfect instruments or incomplete information, but a built-in feature of reality itself. To understand why the electron's probability cloud doesn't simply shrink down to a point on the nucleus, you need to understand a principle that sits at the very heart of quantum mechanics. It's called the Heisenberg uncertainty principle, and it is one of the most misunderstood ideas in all of science. Most people, if they've heard of it at all, think it means something like this. You can't measure something without disturbing it. If you try to look at an electron, the light you use to see it bumps the electron and changes its position. So you can never know exactly where it is because the act of looking moves it. This explanation is common in popular science. It sounds reasonable, and it's wrong. Or at least, it's deeply misleading. The uncertainty principle is not about the clumsiness of measurement. It's not about disturbing particles by looking at them. It's about the fundamental nature of reality itself. It says that certain pairs of physical properties cannot both have precise values at the same time, not because we can't measure them precisely, but because they don't have precise values simultaneously. The universe itself doesn't contain that information. The most important pair of properties governed by the uncertainty principle is position and momentum. Momentum is essentially a measure of how much motion a particle has. It depends on the particle's mass and velocity. The uncertainty principle says that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you can know the other. And this is not a statement about your equipment or your cleverness as an experimenter. It's a statement about reality. If an electron has a very well-defined position, meaning you know almost exactly where it is, then its momentum is fundamentally undefined. It doesn't have a precise momentum, not because you haven't measured it yet, but because a precise momentum doesn't exist for that electron in that state. Conversely, if an electron has a very well-defined momentum, you know almost exactly how fast it's moving and in what direction, then its position is fundamentally spread out. The electron is genuinely delocalized. It exists over a wide region of space, not at any single point. This trade-off is not approximate. It's governed by a precise mathematical inequality. The uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a specific value. That value is Planck's constant divided by 4 pi. You can make one uncertainty smaller, but only at the cost of making the other one larger. You can never make both small at the same time. The product of the two uncertainties has a flaw, a minimum value it cannot go below. No matter what you do, no matter how clever your experiment, no matter how advanced your technology, this is a law of nature as fundamental as the speed of light or the conservation of energy. Now, let's apply this principle to the atom. Imagine you have a hydrogen atom. One proton at the center, one electron somewhere nearby. The proton is positively charged. The electron is negatively charged. The electromagnetic force between them is attractive. the electron is pulled toward the proton. If you think about this purely in terms of energy, it seems like the electron should get as close to the proton as possible. In classical physics, the potential energy of the electron decreases as it gets closer to the nucleus. It's like a ball rolling downhill. The ball rolls toward the lowest point because that's where the gravitational potential energy is minimized. Similarly, the electron should fall toward the nucleus because that's where the electromagnetic potential energy is minimized. If the electron could sit right on top of the proton at zero distance, the potential energy would be at its absolute minimum, maximally negative, as favorable as it could possibly be. So why doesn't it? This is where the uncertainty principle changes everything. Think about what it means for the electron to be right on top of the nucleus. It means the electron's position is known with extraordinary precision. It's confined to an incredibly small volume, essentially the volume of the nucleus, which is about 100,000 times smaller than the atom. But the uncertainty principle says that if you confine the electron's position to a very small region, its momentum becomes highly uncertain. An uncertain momentum doesn't mean the momentum is unknown. It means the momentum can take on a wide range of values. Some of those values will be very large, and large momentum means large kinetic energy. Kinetic energy is the energy of motion. An electron with a lot of momentum is an electron that's moving very fast. And an electron moving very fast has a lot of kinetic energy. So here's the trade-off. If you push the electron closer to the nucleus, you decrease the potential energy. That's favorable. The electron is in a deeper potential energy well, but by confining the electron to a smaller space, you increase its kinetic energy because of the uncertainty principle. That's unfavorable. The electron now has more energy of motion. These two effects work in opposite directions. Decreasing distance lowers potential energy but raises kinetic energy. The total energy of the electron is the sum of both, and the atom will settle into the configuration that minimizes the total energy, not just the potential energy. Let's trace through what happens as you imagine squeezing the electron closer and closer to the nucleus. Start with the electron very far away. At a large distance, the potential energy is nearly zero. The electron barely feels the nucleus. It's not being attracted with much force because the distance is large. The kinetic energy is also low because the electron can be spread over a wide region, meaning the uncertainty in its position is large, meaning the uncertainty in its momentum can be small, meaning the kinetic energy doesn't have to be very high. As you bring the electron closer to the nucleus, the potential energy decreases. The electromagnetic attraction gets stronger. This is favorable. Energy is being released, but at the same time, the electron is being confined to a smaller region of space. Its position uncertainty is decreasing, and by the uncertainty principle, its momentum uncertainty must increase. The minimum kinetic energy the electron must have starts to rise. At first, the decrease in potential energy is larger than the increase in kinetic energy. So the total energy goes down. Getting closer to the nucleus is still energetically favorable. The atom is lowering its energy by shrinking. But as the electron gets closer and closer, the kinetic energy starts increasing faster than the potential energy is decreasing. Remember, the potential energy follows an inverse distance relationship. It decreases as 1 over the distance, but the kinetic energy due to confinement increases much more steeply. It goes roughly as 1 over the distance squared. At large distances, the 1 over distance term dominates, and the potential energy wins. At small distances, the 1/distance squared term dominates, and the kinetic energy wins. There's a sweet spot, a specific distance from the nucleus where the total energy is at its absolute minimum. At this distance, the decrease in potential energy from getting closer is exactly balanced by the increase in kinetic energy from being more confined. Moving the electron any closer would cost more kinetic energy than it would gain in potential energy. Moving it farther away would cost more potential energy than it would save in kinetic energy. This is the ground state of the atom, the lowest possible energy state, the most stable configuration, the resting point. For hydrogen, this optimal distance turns out to be about 53 picometers. That's 53 trillionths of a meter. This distance is called the Bohr radius, named after Niels Bohr because it matches the radius of the innermost allowed orbit in his 1913 model. The fact that the quantum mechanical calculation agrees with Bohr's result is not a coincidence. It's confirmation that both approaches are describing the same underlying physics, just from different angles. But the quantum picture is far richer than Bohr's model. In Bohr's model, the electron is at the Bohr radius, orbiting in a circle at that specific distance. In the quantum picture, the electron is not at any specific distance. It exists as a probability cloud that is densest near the Bohr radius, but extends both closer to and farther from the nucleus. There is actually a non-zero probability of finding the electron very close to the nucleus. There is even a non-zero probability of finding the electron inside the nucleus. But the probability cloud as a whole is centered around the Bohr radius. The most likely distance to find the electron is right around 53 picometers from the proton, and the average distance is close to that value as well. The key insight is this: the ground state is extended. It has spatial size. The electron's probability cloud in the ground state is spread over a region roughly 1/10-billionth of a meter across. That's much larger than the nucleus, which is only about 1 femtometer across, roughly 100,000 times smaller. The electron doesn't collapse to a point on the nucleus because doing so would require confining it to an impossibly small space, which would give it an enormous amount of kinetic energy. The energy cost of that confinement far exceeds the energy benefit of being close to the nucleus. The atom can't shrink below a certain size because quantum mechanics imposes a minimum on how tightly you can squeeze an electron before the energy cost becomes prohibitive. This is fundamentally different from the classical picture in every possible way. In classical physics, the electron spirals into the nucleus because there's nothing to stop it. Energy is radiated away continuously, and there's no floor, no minimum, no limit to how close the electron can get. The spiral continues all the way down to zero distance. In quantum mechanics, there is floor, the ground state, the lowest energy level. The electron cannot go below this state because there is no lower state to go to. You can't extract energy from an electron that's already in its lowest possible energy configuration. It has nowhere to fall. There's no state with less energy for it to transition into. This is often described using the concept of zero-point energy. Even in the ground state, even at the lowest possible energy, the electron still has kinetic energy. It is still, in some sense, moving, not orbiting, not following a path, but its momentum is non-zero. It has to be, because of the uncertainty principle. If the electron were perfectly stationary, meaning zero momentum, its momentum would be known exactly, with zero uncertainty. But then, the uncertainty principle would demand that its position uncertainty be infinite. The electron would be smeared across all of space. That's not a bound atomic state at all. So a bound electron, an electron attached to a nucleus, must always have some kinetic energy. It can never be perfectly still. This residual motion, this 0-point energy, is what prevents the atom from collapsing. It's not a force pushing the electron outward. There is no outward force. The only force is the electromagnetic attraction pulling the electron inward. But the quantum mechanical nature of the electron, specifically the fact that confining it increases its kinetic energy, creates an effective resistance to compression. The atom reaches a minimum size and cannot shrink further. And this 0-point energy isn't just a theoretical prediction. It has observable consequences in the real world. The most striking example is helium. Helium is the only element in the universe that remains a liquid all the way down to absolute zero at normal atmospheric pressure. Every other element freezes solid long before reaching absolute zero. Water freezes at 273 kelvins. Nitrogen freezes at 63 kelvins. Even hydrogen, the lightest element besides helium, freezes at about 14 kelvins. But helium, cooled all the way to absolute zero, stays liquid. It refuses to freeze. The reason is 0-point energy. Helium atoms are very light, and because of the uncertainty principle, their 0-point motion is large enough to prevent the atoms from locking into the fixed positions that a solid crystal requires. Even when you remove every last bit of thermal energy, the helium atoms are still jiggling, still moving, still restless with their irreducible quantum motion. That motion is enough to keep them from settling into a rigid lattice. You can force helium to freeze, but only by applying external pressure, about 25 atmospheres at absolute zero, to physically squeeze the atoms close enough together that the crystal structure can form despite the 0-point motion. At normal pressure, it simply won't happen. This is direct, tangible, laboratory-verified proof that 0-point energy is real. It's not just a mathematical artifact of the equations. It has measurable, physical consequences. The same irreducible quantum motion that keeps helium liquid at absolute zero is the same phenomenon that keeps electrons from collapsing into nuclei. It's the uncertainty principle made visible. It's worth pausing here to address a common misconception. Many explanations of atomic stability say something like the uncertainty principle prevents the electron from being in the nucleus. That's not quite right. The uncertainty principle doesn't forbid the electron from being found at the nucleus. As I mentioned, there is a non-zero probability of finding the electron at the position of the nucleus. In fact, for certain quantum states called s orbitals, the probability density is actually highest right at the nucleus. The electron is most likely to be found at the exact center. This might seem like a contradiction. If the electron is most likely to be found at the nucleus, why hasn't it collapsed into the nucleus? The answer is subtle and has to do with the difference between probability density and probability. The probability density might be highest at the center, but the probability of finding the electron in any tiny volume depends on both the probability density and the size of that volume. Near the nucleus, the volume is extremely small. Think of it this way. Imagine a spherical shell around the nucleus at a certain distance. The probability of finding the electron in that shell depends on two things: the probability density at that distance and the surface area of the shell. Close to the nucleus, the probability density is high, but the surface area of the shell is tiny because the shell has a very small radius. Far from the nucleus, the surface area is large, but the probability density has dropped off. The most probable distance, the distance where you're most likely to find the electron, is where the product of probability density and surface area is maximized. For the hydrogen ground state, this most probable distance is exactly the Bohr radius, 53 picometers. The electron isn't barred from being at the nucleus. It's just that the quantum state as a whole is spread out. The probability cloud has a characteristic size, and that size is much larger than the nucleus. The electron visits the nucleus, so to speak, but it doesn't live there. Its quantum state is extended over a much larger region. And this extended state is the ground state, the lowest energy configuration. The state the atom naturally relaxes into. You cannot make it smaller without adding energy. There's another way to think about this that might help. Think about what the electron's wave function looks like. In the ground state of hydrogen, the wave function is a smoothly declining exponential centered on the nucleus. It's largest at the center and fades away with distance. The characteristic decay length is the Bohr radius. Now imagine trying to squeeze this wave function into a smaller space. You want to confine the electron closer to the nucleus. To do this, the wave function has to be more sharply peaked. It has to rise and fall more steeply over a shorter distance. But a more sharply peaked wave function means a higher spatial frequency. And higher spatial frequency means higher momentum. And higher momentum means higher kinetic energy. This is the wave mechanics version of the uncertainty principle. Confining a wave to a smaller space requires shorter wavelengths, which means higher frequencies, which means higher energy. You can see this with any wave. A guitar string vibrating in its fundamental mode has a long wavelength and a low frequency and a low energy. Vibrating in higher harmonics produces shorter wavelengths, higher frequencies, and more energy. It takes more energy to sustain these higher modes. The same principle applies to the electron wave. Squeezing it into a smaller space requires higher energy modes. The atom settles into the mode that balances the desire to be close to the nucleus against the cost of confinement. And now let me connect this back to the broader question of why electrons don't fall into the nucleus. The answer has three parts, and all three are essential. First, the electron does not orbit the nucleus along a classical trajectory. It exists in a quantum state, a standing wave pattern described by the Schrödinger equation. Because it has no trajectory, the classical argument about accelerating charges radiating energy does not apply. Second, the quantum states of the electron come in discrete energy levels. The electron can only exist in certain allowed states, each with a specific energy. It cannot exist between these states. It cannot gradually lose energy by radiating continuously. It can only jump between states by emitting or absorbing a photon with exactly the right energy. Third, the lowest energy state, the ground state, has a finite spatial extent determined by the balance between electromagnetic potential energy and quantum kinetic energy. The electron cannot go below this state because there is no state with lower energy. The ground state is the floor. The electron has nowhere to fall. Together, these three features of quantum mechanics completely resolve the problem that classical physics could not solve. The atom is stable because the electron exists in a quantum state, because those states are quantized, and because the lower state is still spatially extended and cannot collapse further. There is a beautiful self-consistency to this picture. The same theory that explains why the electron doesn't collapse also explains the specific sizes of atoms, the specific energies at which atoms emit and absorb light, and the specific chemical properties of elements. Everything flows from the same quantum mechanical framework. Every atom of a given element is identical. Every hydrogen atom in the universe has exactly the same ground state energy, exactly the same size, exactly the same spectral lines. This is not something classical physics could explain. In classical physics, there was nothing special about any particular orbit. An electron could orbit at any distance with any energy. There was a continuum of possibilities. Two hydrogen atoms formed at different times in different places could be completely different in size, energy, and behavior. But quantum mechanics says no. The allowed states are determined by the Schrödinger equation and the properties of the proton and electron. Since all protons are identical and all electrons are identical, all hydrogen atoms must have exactly the same set of allowed states. There's no room for variation. Every hydrogen atom is a perfect copy of every other hydrogen atom. This uniformity is essential for the universe to work the way it does. Chemistry depends on atoms having consistent, predictable properties. Biology depends on chemistry. The fact that carbon always behaves like carbon, that oxygen always behaves like oxygen, that hydrogen always behaves like hydrogen, these are not accidental. They're guaranteed by quantum mechanics. If atoms could have any size and any energy, the universe would be chaotic. Every atom would be different. Chemical reactions would be unpredictable. Molecules couldn't form reliably. Life as we know it would be impossible. But because quantum mechanics enforces specific, discrete, universal energy levels, atoms are reliable. Chemistry is consistent. The building blocks of matter are standardized. And complexity, including the staggering complexity of life, becomes possible. I also want to address something that might be nagging at you. If the electron can't fall below the ground state in an isolated atom, what about extreme conditions? What happens when you subject atoms to enormous pressures or extreme environments? Can you force the electron into the nucleus? The answer is yes, in a sense. Under extreme conditions, electrons can be pushed into nuclei. This process is called electron capture, and it's a real phenomenon observed in certain radioactive atoms. In electron capture, a proton in the nucleus absorbs an inner electron and converts into a neutron, releasing a neutrino in the process. This changes the identity of the atom. An element with one more proton becomes an element with one fewer proton. For example, when beryllium-7 undergoes electron capture, a proton absorbs an electron and becomes a neutron. The beryllium atom, which has 4 protons, becomes a lithium atom, which has 3 protons. This isn't the electron spiraling in classically. It's a quantum mechanical process that relies on the fact that the electron's probability cloud does extend to the nucleus. There is a tiny but non-zero probability that the electron will be found right at the proton's location, and when it is, the weak nuclear force can facilitate the conversion. The probability is small, which is why electron capture is a relatively slow process compared to other nuclear reactions. But it happens. It's real, and it demonstrates that quantum mechanics doesn't erect some sort of impenetrable wall between the electron and the nucleus. There's no force pushing the electron away. The electron simply has a quantum state that is mostly extended over a region much larger than the nucleus. Even more dramatic is what happens when a massive star dies. If the remnant core is heavy enough, gravity can overwhelm the quantum mechanical ground state entirely. The gravitational energy becomes so immense that it pays the full cost of confinement, crushing electrons into protons across the entire collapsing core and destroying every atom in the process. The quantum floor that held for billions of years is broken through by sheer gravitational force. It takes the death of an entire star to do it, and when it happens, matter is compressed into forms so extreme they barely resemble anything we encounter on Earth. But even those exotic remnants are still governed by quantum rules, as we're about to see. Under any normal circumstances, though, none of this happens. The quantum mechanical ground state holds. Atoms remain stable. Electrons remain in their extended probability clouds. And matter maintains the structure and properties that make the universe as we know it possible. The stability of atoms is not fragile. It's incredibly robust. Atoms survive collisions, chemical reactions, high temperatures, intense radiation, and the passage of billions of years without their fundamental structure changing. A hydrogen atom today is identical to a hydrogen atom that formed 13.8 billion years ago, in the first minutes after the Big Bang. The quantum mechanical ground state has held for the entire age of the universe, and it will continue to hold for as long as the laws of physics remain unchanged. This robustness is itself a consequence of quantization. Because the energy levels are discrete, with finite gaps between them, it takes a specific minimum amount of energy to disturb an electron from its ground state. Random thermal jostling at low temperatures doesn't provide enough energy to excite the electron. The atom simply stays in its ground state, impervious to minor perturbations. Only when the environment provides enough energy to bridge the gap between energy levels can the electron transition to a higher state. And even then, it quickly returns to the ground state by emitting a photon, falling back to its stable configuration. The atom is like a ball sitting at the bottom of a bowl. Small pushes cause it to roll around a bit, but it always returns to the center. You need a sufficiently strong push to knock it out of the bowl entirely. The discrete energy levels of the atom provide that bowl, and the ground state is the very bottom. This is the complete quantum mechanical answer to why the electron doesn't fall into the nucleus. It's not because of a repulsive force. It's not because the electron is moving too fast. It's not because of angular momentum keeping it in orbit like a satellite. The real answer is that the electron is a quantum object, whose behavior is governed by wave mechanics, whose states are quantized into discrete energy levels, and whose ground state is spatially extended, because the uncertainty principle prevents infinite confinement without infinite energy. The atom doesn't collapse, because quantum mechanics provides a flaw that classical physics does not have. Let's step back now and think about what all of this means. Not just for physics, not just for the abstract question of why electrons don't crash into nuclei, but for everything. For the chair you're sitting in, for the air filling your lungs, for the blood moving through your veins, for the stars burning in the sky tonight, for the entire visible universe and every structure in it. Because the stability of the atom is not a footnote in a physics textbook. It is the single most important structural fact about the universe. Without it, there is no universe. Not the universe we know, not a universe with stars or planets or water or rock or light or life. Without stable atoms, there is nothing but a featureless soup of collapsed particles, incapable of forming structures, incapable of chemistry, incapable of complexity of any kind. Every object you have ever touched, every substance you have ever tasted, every material you have ever seen, exists because electrons occupy stable quantum states around nuclei. The hardness of diamond, the softness of cotton, the transparency of glass, the conductivity of copper, the flexibility of rubber. Every single material property of every substance in existence traces back to how electrons arrange themselves in quantum states around atomic nuclei. And those arrangements are possible only because quantum mechanics prevents the atom from collapsing. Consider what happens when atoms interact with each other. When two atoms come close together, their electron clouds overlap. The electrons from one atom begin to feel the presence of the other atom's nucleus and electrons. Depending on the specific atoms involved and the specific quantum states their electrons occupy, several things can happen. The atoms might repel each other. Their electron clouds push against each other, and neither atom is willing to rearrange its electrons to accommodate the other. The atoms bounce apart, or the atoms might attract each other. The electrons might rearrange themselves into new quantum states that encompass both nuclei simultaneously. When this happens, the electrons are shared between the two atoms. This sharing lowers the total energy of the system. The two atoms together have less energy than they would separately. This means the combined state is more stable. The atoms stick together. This is a chemical bond. And chemical bonds are what build molecules. Molecules are groups of atoms held together because their electrons have found quantum states that span multiple nuclei, states that are lower in energy than the states the electrons would occupy if the atoms were separate. Every molecule in existence, from the simplest hydrogen molecule with just two atoms to the most complex protein with thousands, is held together by electrons in shared quantum states. The water molecule is a perfect example. Two hydrogen atoms and one oxygen atom come together. The oxygen atom has 8 electrons. 2 of them sit in the innermost energy level, close to the oxygen nucleus, and they don't participate much in bonding. Of the remaining 6, 2 rearrange into shared quantum states with the hydrogen atoms, one electron pairing with each hydrogen's single electron to form 2 covalent bonds. The other 4 remain on the oxygen as lone pairs, influencing the molecule's shape. The result is a bent molecule with specific bond angles, specific bond lengths, and specific properties that make water the extraordinary substance it is. Water's ability to dissolve other substances, its high heat capacity, its expansion when it freezes, its surface tension, all of these properties come directly from the quantum mechanical arrangement of electrons in the water molecule. And all of these properties depend on the stability of the atoms that make up the molecule. If hydrogen atoms were unstable, if their electrons collapsed into their protons, there would be no hydrogen atoms to bond with oxygen. There would be no water. There would be no oceans, no rivers, no clouds, no rain. There would be no medium for the chemical reactions that sustain life. The periodic table of elements is another direct consequence of quantum mechanical atomic stability. Every element in the periodic table is defined by the number of protons in its nucleus. Hydrogen has 1, helium has 2, carbon has 6, iron has 26, uranium has 92. Each element has a specific number of electrons equal to the number of protons in a neutral atom, and those electrons arrange themselves in quantum states according to precise rules. The arrangement of electrons determines everything about how an element behaves. It determines which other elements it bonds with, how strongly, in what configurations. It determines whether an element is a metal, a non-metal, or a metalloid, whether it's a gas, a liquid, or a solid at room temperature. whether it conducts electricity or insulates against it, whether it's reactive or inert. And the rules governing this arrangement come from quantum mechanics. Specifically, they come from the quantum mechanical properties of electrons and atoms, the allowed energy levels, the shapes of the orbitals, and a principle I haven't discussed yet but which is absolutely crucial: the Pauli exclusion principle. The Pauli exclusion principle was formulated by Austrian physicist Wolfgang Pauli in 1925. It states that no two electrons in an atom can occupy the same quantum state simultaneously. Each electron must have a unique set of quantum numbers. Each quantum state can hold at most one electron with a given spin orientation. And since electrons can spin in two directions, each orbital can hold at most two electrons. This principle has staggering consequences. Without it, all electrons in an atom would collapse into the lowest energy orbital, the ground state. Every atom, regardless of how many electrons it had, would have all its electrons packed into the same innermost shell. All atoms would have essentially the same size and the same chemical properties. There would be no periodic table, no diversity of elements, no chemistry as we know it. Carbon would behave exactly like oxygen, which would behave exactly like iron, which would behave exactly like gold. Everything would be the same because every atom's electrons would be in the same state. But the Pauli exclusion principle prevents this. Because each quantum state can hold only two electrons, the electrons in a multi-electron atom must stack up into progressively higher energy levels. The first two electrons fill the lowest orbital. The next two fill the next orbital. Then the next six fill a set of three higher orbitals, and so on, building outward layer by layer. This layered structure gives atoms their size. The outermost electrons, the ones in the highest occupied energy levels, determine the atom's effective radius. Because the Pauli exclusion principle forces electrons into higher and higher levels, atoms are much larger than they would be if all electrons could occupy the ground state. And this is directly why solid matter has the properties it does. This is why you don't fall through the floor. When you stand on the ground, the atoms in your shoes are pressing against the atoms in the floor. The electron clouds of those atoms overlap slightly. And the Pauli exclusion principle prevents the electrons from being compressed into the same quantum states. The electrons resist being pushed together. Not because of electromagnetic repulsion, although that plays a role too, but because the laws of quantum mechanics literally forbid them from occupying the same states in the same space. This resistance to compression is what gives solid matter its rigidity. It's what makes walls solid, what makes steel strong, what makes the ground hold you up. Without the Pauli exclusion principle, matter would have no resistance to compression. Everything would collapse into an extremely dense state. There would be no solid objects, no surfaces, no structures. The universe as we know it would not exist. Now, here's something remarkable. The Pauli exclusion principle applies specifically to a class of particles called fermions. Electrons are fermions, so are protons and neutrons. In fact, all the particles that make up ordinary matter are fermions. There's another class of particles called bosons, which include photons, the particles of light. Bosons do not obey the Pauli exclusion principle. Multiple bosons can and do occupy the same quantum state simultaneously. This is why lasers work. A laser produces coherent light, which means billions of photons all in the same quantum state, marching in lockstep. Fermions can never do this. Electrons can never pile up in the same state. And that fundamental difference between fermions and bosons is what gives matter its structure. Light can pile up, matter cannot. This distinction shapes the entire universe. Let me take you even further. Let's talk about what happens when the quantum stability of atoms is pushed to its absolute limit. Because the universe does contain environments where the normal quantum structure of atoms breaks down, and what happens in those environments tells us even more about why atomic stability matters. When a star like the Sun exhausts the hydrogen fuel in its core, it begins to die. The core contracts under its own gravity, and the outer layers expand enormously, turning the star into a red giant. Eventually the outer layers are expelled, and what remains is the core. A dense, hot remnant called a white dwarf. A white dwarf is extraordinary. It has roughly the mass of the Sun compressed into a sphere about the size of the Earth. The density is about 1,000,000 times greater than the density of water. A teaspoon of white dwarf material would weigh roughly 5 tons. At these densities, individual atoms can no longer maintain their normal structure. The electron clouds of neighboring atoms are compressed into each other. The electrons are squeezed into a much smaller volume than they would normally occupy. But the electrons can't all collapse into the lowest energy states because of the Pauli exclusion principle. Each electron must occupy a different quantum state. And as the available volume shrinks, the electrons are forced into higher and higher energy levels with greater and greater momentum. This creates an outward pressure called electron degeneracy pressure. It's not a pressure caused by heat or by electromagnetic repulsion. It's a purely quantum mechanical pressure arising from the fact that electrons are fermions and cannot share quantum states. This degeneracy pressure is what holds the white dwarf up against the crushing force of gravity. Without it, the star would continue collapsing. The white dwarf is a macroscopic object whose very existence depends on the Pauli exclusion principle, the same quantum rule that gives ordinary matter its rigidity, that prevents you from falling through the floor, is holding up an entire dead star against gravitational collapse. But there's a limit. In 1930, a young Indian physicist named Subrahmanyan Chandrasekhar showed that electron degeneracy pressure can only support a white dwarf up to a certain mass, about 1.4 times the mass of the Sun. This is called the Chandrasekhar limit. If the remnant core of a dead star exceeds this mass, electron degeneracy pressure isn't strong enough to resist gravity. The electrons are forced into the protons, combining with them to form neutrons. The entire star collapses further, becoming a neutron star. A neutron star is even more extreme than a white dwarf. It has the mass of 1 to 2 suns compressed into a sphere about 12 miles across. The density is about 100 trillion times the density of water. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. At these densities, atoms don't exist anymore. The electron clouds have been completely destroyed. The electrons have been absorbed into the protons. What remains is essentially a giant ball of neutrons, held up by neutron degeneracy pressure, which is the same Pauli exclusion principle applied to neutrons instead of electrons. And even neutron degeneracy pressure has its limits. If the mass of the collapsing core exceeds about 2 to 3 times the mass of the Sun, even neutron degeneracy pressure fails. Nothing can resist the gravitational collapse. The matter falls inward without limit, forming a black hole, a region of space where gravity is so extreme that nothing, not even light, can escape. In a black hole, the quantum mechanical stability that we've been talking about has been completely overwhelmed. The atoms are gone, the electrons are gone, the neutrons are gone. All the structure that quantum mechanics provided has been crushed out of existence by the sheer force of gravity. What remains is a singularity, a point of theoretically infinite density where our current understanding of physics breaks down. The progression from white dwarf to neutron star to black hole is a story about the limits of quantum stability. The same quantum mechanics that keeps ordinary atoms stable, that prevents electrons from falling into nuclei, that gives matter its structure and rigidity, can be overwhelmed under extreme enough conditions. But those conditions are extreme beyond anything we encounter in everyday life. They require the gravitational collapse of an entire star. Under any normal circumstances, under any conditions you will ever experience on Earth, quantum mechanical atomic stability holds absolutely. Your atoms are not in danger of collapsing. Not now, not ever. Not unless you happen to fall into a neutron star or a black hole. Let's come back down to Earth now, literally, and think about what all of this means for you. You are made of atoms, roughly 7 billion of them. 7 followed by 27 zeros. Every one of those atoms is stable. Every one of them has electrons sitting in well-defined quantum states around a nucleus. Every one of them has a ground state energy that it will never fall below under normal conditions. The atoms in your body include hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, and traces of dozens of other elements. The hydrogen atoms were mostly formed in the first few minutes after the Big Bang, about 13.8 billion years ago. The heavier elements, the carbon and oxygen and nitrogen that make up most of your body's mass, were forged inside stars that lived and died billions of years before the Sun and Earth formed. Those stars fused lighter elements into heavier ones in their cores, hydrogen into helium, helium into carbon, carbon into oxygen. And when those stars exploded as supernovae, they scattered these heavy elements across space. Eventually, some of those atoms ended up in the cloud of gas and dust that collapsed to form our solar system about 4.6 billion years ago. The heavier atoms became part of the rocky material that formed Earth. And over billions of years of geological and biological evolution, some of those atoms became part of you. Every atom in your body has a history stretching back billions of years. And throughout that entire history, those atoms have been stable. Their electrons have remained in quantum states around their nuclei. They haven't collapsed. They haven't degraded. They've been recycled through stars, through supernova explosions, through molecular clouds, through the formation of the solar system, through the geology of Earth, through the biology of countless organisms, and now through you. And at every step, at every moment, in every environment they've passed through, the quantum mechanical stability of those atoms has held. The ground state has persisted. The electrons have remained in their probability clouds. The atoms have maintained their identities and their properties. This is not something you normally think about. You go about your day, touching objects, breathing air, eating food, without ever considering that the solidity of every surface, the transparency of every window, the taste of every meal, the color of every flower, the warmth of sunlight on your face, all of it depends on quantum mechanics. All of it depends on electrons occupying stable quantum states around nuclei. All of it depends on the fact that the atom does not collapse. Take a breath right now. Feel the air entering your lungs. That air is made of molecules, nitrogen molecules, each consisting of 2 nitrogen atoms bonded together by shared electrons, oxygen molecules, each consisting of 2 oxygen atoms bonded the same way. These molecules exist because nitrogen and oxygen atoms are stable. Their electrons are in well-defined quantum states that allow specific bonding patterns. The oxygen molecules in that breath will pass through your lung membranes into your bloodstream, carried by hemoglobin molecules in your red blood cells. Hemoglobin is a protein made of thousands of atoms, carbon, hydrogen, oxygen, nitrogen, and a few iron atoms at the center. The iron atoms are crucial. They're the ones that actually bind the oxygen. And the ability of iron to bind oxygen depends entirely on the specific quantum states of iron's electrons. Different electron configurations lead to different bonding properties. Iron's electron configuration gives it exactly the right chemistry to bind oxygen loosely enough to pick it up in the lungs and release it in the tissues. If iron's quantum states were different, hemoglobin wouldn't work. Oxygen transport in your blood would fail. You would die. Your survival depends, literally and directly, on the specific quantum mechanical properties of iron atoms, on the specific energy levels and orbital shapes that iron's 26 electrons occupy, on the stability of those states, on the fact that iron atoms don't collapse. Every heartbeat, every thought, every sensation you experience is electrochemistry. The movement of ions through cell membranes, the transmission of electrical signals along nerves, the release and uptake of neurotransmitters at synapses. All of it is quantum mechanics in action, not in some exotic or dramatic way, in the most fundamental way possible. The atoms doing the work are stable. Their electrons are in well-defined quantum states. Their chemical properties are consistent and predictable, and therefore, biology works. Let's zoom out one more time. Stars shine because of quantum mechanics. The fusion reactions that power stars depend on a quantum phenomenon called quantum tunneling. And this phenomenon deserves a closer look because it reveals just how deeply quantum mechanics is woven into the fabric of the cosmos. In the core of the sun, hydrogen nuclei, which are just protons, are moving at high speeds due to the extreme temperature, about 15 million degrees. At these temperatures, protons are moving at hundreds of kilometers per second, crashing into each other billions of times every second. But even at these enormous speeds, the protons don't have enough energy to overcome the electromagnetic repulsion between them. Two protons are both positively charged, and like charges repel. As two protons approach each other, the repulsive force between them gets stronger and stronger. It's like trying to push two powerful magnets together with the same poles facing each other. The closer you push them, the harder they push back. For two protons to fuse, they need to get close enough for the strong nuclear force to take over. The strong force is extremely powerful, far stronger than the electromagnetic force, but it only operates at very short range, about 1 femtometer, 1 quadrillionth of a meter. Beyond that distance, it's essentially invisible. The protons have to get that close before the strong force can grab them. But the electromagnetic repulsion creates an energy barrier. To overcome it classically, the protons would need to be moving much faster than they actually are. Even at 15 million degrees, the thermal energy of the protons provides only about 1% of the energy needed to climb over this barrier. Classically, the protons would bounce off each other every single time. They would never get close enough to fuse, not once, not in a billion years. The sun would be cold and dark, But quantum mechanics changes the rules. Because protons are quantum objects described by wave functions, their positions are not precisely defined. The proton's wave function doesn't stop abruptly at the energy barrier the way a classical particle would. Instead, the wave function extends into and through the barrier, fading exponentially as it goes, but never reaching exactly zero. On the other side of the barrier, in the region where the strong force dominates, the wave function has a small but non-zero value. This means there is a small but non-zero probability that the proton will simply appear on the other side of the barrier, even though it never had enough energy to climb over it. The proton doesn't go over the barrier. It doesn't go around it. It goes through it, like a ghost walking through a wall. This is quantum tunneling, and the probability of it happening in any single collision is absurdly low. For 2 protons in the sun's core, the probability that tunneling will occur in any given collision is roughly 1 in 10 to the 28th power. That's 1 chance in 10 billion billion billion. Those are terrible odds. If you were betting on any one particular pair of protons fusing, you would wait an extraordinarily long time. But here's what makes it work. The sun is enormous. Its core contains an almost incomprehensible number of protons. About 10 to the 57th protons are packed into the core, all moving at high speed, all colliding with each other constantly. The number of proton-proton collisions happening every second in the sun's core is staggering. Roughly 10 to the 38th collisions per second. When you multiply a tiny probability by an astronomical number of attempts, you get a substantial result. Even though each individual collision has almost no chance of producing fusion, the sheer number of collisions means that roughly 90 trillion complete fusion chains occur in the sun's core every single second. Each one releases only a tiny amount of energy. But multiplied across that staggering number of reactions, the total output is about 3.8 times 10 to the 26th watts of power. Enough to sustain the sun's luminosity, to warm our planet, to power photosynthesis, to drive the climate, to make life possible. All of it depends on quantum tunneling. All of it depends on the fact that a proton's wave function doesn't stop at the energy barrier, but leaks through it. If quantum mechanics didn't exist, if protons were classical billiard balls that either had enough energy to overcome the barrier or didn't, fusion in the sun would never occur. Not slowly, not inefficiently, never. The sun would never have ignited. The stars would be dark. The universe would be a cold, lifeless void of hydrogen and helium gas, slowly cooling toward absolute zero. No light, no heat, no heavy elements, no planets, no chemistry, no life. The same quantum mechanics that keeps atoms stable also makes stars shine. So the same quantum mechanics that keeps atoms stable also powers the stars. The same framework that prevents electron collapse also enables nuclear fusion. The same principles that give matter its structure also provide the energy source that drives the entire cosmos. And there's an even deeper symmetry here. The elements forged in stars through quantum tunneling are the same elements whose atoms are stable because of quantum mechanics. Quantum mechanics builds the atoms. Quantum mechanics powers the stars that forge those atoms. Quantum mechanics governs the chemistry that assembles those atoms into molecules and materials and living organisms. And quantum mechanics keeps all of it stable, preventing the atomic collapse that would otherwise destroy everything. Everything connects. The stability of the atom is not an isolated fact about physics. It's the foundation on which the entire structure of the universe rests. From the largest star to the smallest bacterium, from the hottest plasma to the coldest ice, everything that exists in the form we recognize depends on electrons not falling into nuclei. We started this journey with the simple question: why don't electrons fall into the nucleus? The classical picture of the atom, with tiny electrons orbiting a central nucleus like planets around a star, predicted that they should. An orbiting electron is an accelerating charge. An accelerated charge must radiate energy. An electron that radiates energy spirals inward. And the math said this collapse should happen in roughly 1/10-billionth of a second. Every atom in the universe should have self-destructed almost instantly. But atoms didn't collapse. They're stable. Fantastically, stubbornly, persistently stable. And the reason we now know is that the classical picture was fundamentally wrong. Electrons don't orbit nuclei. They don't follow trajectories. They don't have definite positions at each moment in time. Instead, they exist in quantum states, described by the wave functions that assign probabilities to different outcomes of measurement. These quantum states are quantized, meaning only specific discrete energy levels are allowed. And the lowest of these levels, the ground state, is spatially extended, spread over a region much larger than the nucleus. The electron can't collapse to a point on the nucleus because confining it that tightly would require more energy than the universe can provide to that electron. The uncertainty principle ensures that squeezing an electron into a smaller space demands ever greater kinetic energy. The ground state represents the perfect balance between the electromagnetic attraction pulling the electron inward and the quantum kinetic energy resisting confinement. This is the floor, the bottom, the lowest rung of the energy ladder. There is nowhere further to fall. And so the atom endures, stable, reliable, unchanged across billions of years. The same today as it was moments after the Big Bang. The same on Earth as on a planet orbiting a distant star in another galaxy. Quantum mechanics doesn't just explain why the electron doesn't fall in. It reveals that the very question assumes a picture of reality that doesn't apply at the atomic scale. The electron never orbited. It never had a trajectory to spiral along. The question itself dissolves when you understand what atoms actually are. And what atoms actually are, what they've been all along, is quantum objects. Objects governed by rules so different from our everyday experience that it took the combined genius of Planck, Einstein, Bohr, de Broglie, Heisenberg, Schrödinger, Born, Pauli, and Dirac to work them out. Rules that replace certainty with probability, trajectories with wave functions, and continuous energy with quantized levels. Rules that are strange, counterintuitive, and philosophically unsettling, but also spectacularly, triumphantly correct. Every prediction quantum mechanics has ever made has been confirmed by experiment. Every atom it says should be stable is stable. Every spectral line it predicts is observed at exactly the right wavelength. Every material property it calculates matches what we measure in the lab. Quantum mechanics is the most precisely tested and most thoroughly confirmed theory in the history of science. And at its core, at the very heart of everything it tells us, is this one simple, profound, world-sustaining fact. The electron does not fall into the nucleus, not because something stops it, but because the universe, at its deepest level, doesn't work the way we once imagined. Reality is quantum, and quantum reality holds. Tonight, when you go to sleep, think about this. Every atom in your pillow is stable. Every atom in the walls around you is stable. Every atom in your body, in your brain, in the neurons firing right now as you process these words is stable. Not because of some delicate balance that might tip over, but because the laws of quantum mechanics are as firm and unyielding as any law of nature can be. The universe rests on a quantum foundation, and that foundation is unshakable. You exist because of it. Stars shine because of it. Chemistry works because of it. Matter itself is possible because of it. Every atom in the cosmos is a testament to the quantum rules that govern the smallest scales of reality. The electron doesn't fall into the nucleus. And because it doesn't, everything else, absolutely everything, is possible. Thank you for joining me on this journey into the heart of the atom. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the physics that shapes our universe. And the next time someone asks you why matter is solid, why atoms are stable, why the universe exists in the form it does, you'll know the answer. Quantum mechanics. The deepest, strangest, most beautiful set of rules nature has ever revealed to us. Good night, and may you never look at an atom the same way again.